My name's Simon Davidmann, so I'm going to be providing a lot of the information in this tutorial this morning. This afternoon for me, I'm in UK, so welcome from whichever part of the world you're in. So we've got a 2-hour session now, which is going to start with some slides, and then we've got Lee's going to be giving a demonstration. This is pre-recorded, so I'll be online on the chat. I did notice that it did say that we'll answer the messages at the chat at the end, but if there's something that I can put stuff in the chat in there. So I don't know, I can't see the main screen here, but I think we're probably ready to go with the video. So thanks very much. Please look at the chat if you want to ask questions. Otherwise, enjoy the show, and we'll talk to you at the end. And keep an eye out at the end, because we've got a giveaway that we've got some information on that, so near the end of the presentation. So thanks very much for joining us, and let's get on with the show.
Hello, my name is Simon Davidmann. I'm the CEO of Imperas Software. And today at DVCon, I'm going to be talking to you about RISC-V processor verification and how we've seen the technologies and techniques people have been using.
Hello, it appears to have stopped.
Yeah, it stopped for us as well.
Hello, my name is Simon Davidmann. I'm the CEO of Imperas Software. And today at DVCon, I'm going to be talking to you about RISC-V processor verification and how we've seen the technologies and techniques people have been using evolve over the last few years to verify processors. So I'm going to be talking about some of the background of introducing the technology, and then my colleague Lee Moore, also from Imperas, is going to give you a 30-minute demonstration and a detailed walkthrough of the use of some verification technology with an open source core. So the focus of this tutorial is really to talk about RISC-V and the fact that RISC-V is changing the options that SoC designers have, because anybody can now design a processor. You can pick up open source, you can modify it, you can change it, you can license IP from people and then modify it. So anybody can become an architecture licensee here. And if you develop your own processor, you need to verify it. And it's not like buying in pre-verified IP. You are going to have to do the verification of it. And most likely, this is going to be new to you. You're going to be doing CPU verification for the first time, because traditionally this has always been done in closed doors in proprietary commercial companies. So this presentation aims to introduce the main approaches that people have been using for CPU DV around RISC-V. We discuss the pros and cons of the different approaches and try and introduce the main components needed in any RISC-V processor design verification environment. So in this tutorial, what are you going to take away from it? What are we going to try and cover? Well, we're going to start and talk a little bit about RISC-V, where it came from, and introduce it and where people are seeing that it's going and how it's being adopted. We're then going to talk about the issues around verifying a CPU, and then cover the different approaches that there are that people have been using for RISC-V. We're then going to drill down into different components in verification test benches, introduce some of the simulators available, both free and commercial. Then we're going to talk about the different components that you might need in your virtual platforms or your simulation for your verification. We're going to talk about the reference models that are available out there and the capabilities that are needed, introduce tests and stream generators, instruction stream generators, talk a little bit about verification in relationship to compliance, and provide a detailed walkthrough of a SystemVerilog test bench verifying an open source core. So first, let's just talk a little bit about Imperas. So we're a company that develops simulators. We develop technology around those simulators, and we develop the models that run on those simulators. And the whole goal is to help people get their systems up and running, their embedded systems running, to get the software running on it, but also to get the hardware guys to get their hardware designs correct, very much into the verification space. Our background, we're 14 years old, we're self-funded, profitable, UK-based with a team in California and a variety of people in other places as well. And much of our background is EDA with simulers and verification, but also processors embedded. We've got staff that have worked in a variety of the main processor companies, but also in terms of the EDA companies. And we've been involved in the development of Verilog, Verilog simulators, the evolution of SystemVerilog, and verification technologies and methodologies. And we started in RISC-V. We started hearing about RISC-V in 2016. We started working with customers in 2017. We got involved with the RISC-V compliance group since 2018, and been working in that since basically so 2017 we started really. And our focus now for RISC-V is CPU verification. One of the things we do is provide configurable reference model and simulators. And the reference model can be configured to anything that's legal in the RISC-V specifications. We provide the reference model, the simulators that run it, and also tools on top of it that allow you to see how it's working, understand its performance, and to help verify it. So it's absolutely, Imperas, we have the best verification solution for RISC-V hardware out there, and it's in use with many of the leading RISC-V CPU developers at the moment. Now, in terms of an agenda, we're going to start with a brief introduction to RISC-V, talk a little bit about it, so to get you up to speed of where it is, and then really focus on the CPU hardware and the DV approaches that people are using to get products of quality developed. And then we're going to drill down into the components of a DV environment with some detailed examples, and then cover other components around the specific DV environment, for example, stream generators. And for each topic, as we introduce and demo the technologies, we're going to give you a feel for the current state of the art of what people are currently doing with things. And we're going to walk through some of the open source solutions that are out there. So let's get started. So RISC-V history. So it's pronounced RISC-V, not RISC-V. It's an open standard instruction set. Started in California, Berkeley in 2010. Many people have been developing computer architectures for years and evolved to sort of RISC, reduced instruction set principles, and that's where that project came from. One of the key differences between RISC-V and other IC design is provided under an open source licenses. So there's no fee to use it, no proprietary technology involved in it. And it's not really just an academic process and academic design. It's now being taken on by a lot of other people outside the universities, obviously. And its goal is about simplicity and for it to be used practically and commercially. Okay. Now, what RISC-V does is it gives you freedom because you can do pretty much anything you want. You can change anything you want and do what you need with it. But when you get freedom, you get a huge challenge in verification. And it's probably, in terms of the verification world that we live in, it's probably the biggest challenge and change that we've had since I don't know when. It's a huge tsunami of challenge that's coming for us all. And why does this come? Where does this come about from? Well, whenever you add a choice in your design or add a new feature, you have to be very, very careful because there's tremendous costs associated with it. And every architecture team knows that as you add a feature, you have to do much more verification and you're adding much more complexity. So that the cost of adding simple features is huge. And especially if you're a relatively inexperienced team in there. It seems easy, oh, well, if we'll just add a few more things here or there, things get more complex. You have to do much more verification. And you end up adding schedule, resources, and quality challenges in there. So there's huge risks in this freedom that you have. And part of the challenge is that as of last year, there is no off-the-shelf toolkit that you can go out and buy. If you want to build a chip, you choose on your HDL, you choose on your synthesis tool, you choose on your simulators, you choose on your formal tools, you choose these different things, and you just go buy the technology. But as of last year, there's no off-the-shelf toolkit to help you with processor DV. There's no EDA company you can go to say, hey, give me a kit to verify my processor. There's all sorts of solutions for this block or that block, but not for processors. And that's traditionally because it's all been done in-house proprietarily by the big processor vendors. Why would they share it? It's a very important part of their solution is the quality of their processors. So there's lots of in-house proprietary solutions, but you've got to get one. If you're going to build your own RISC-V processor, you've got to build a verification environment. And this is going to add a lot to the schedule, resources, and costs and risks in there. And already, if you buy in a CPU, your overall SoC cost, half of it is in the verification of it. And now you've got the extra challenge of bringing in a processor DV as well, so it's adding tremendously to the schedules that people have and the resources they need in building SoCs. And in terms of a project sort of timeline, if you want to do processor DV, what do you need to do? Well, the first thing you have to do is you're going to have to get a team together. Okay, this is when we talk to customers. It's what do you need to do to get processor DV done? First is you need an expert team to get on with the verification, and you need to work out what it is you want to be verified and develop these metrics in there. And one of the most important things you need to do is to develop a verification plan with these metrics in it, so you know exactly what it is that you're trying to get to, the quality that you're trying to get to, the areas that you've got to verify and test. And that is what your measurements you're going to have to measure. And then you have to, once you've got a plan, you've got some of the people and the team, you need to actually get the technology in place. You need to decide which EDA tools and models and methods are going to be used, what simulators are going to do, whether you can use open source technologies, or whether you can use commercial or consultants, whether you can use SystemVerilog and UVM or do it in emulators and FPGAs and things, whether you're going to use formal tools or just simulation. Then you've got to start bringing it all inside and getting up to speed with it, maybe buying some verification IP, get things up and running. Then you've got to get the tests, create tests. Most likely you're going to create your own tests with a constrained random generator, an awful lot of those, and then you're going to find issues where your RTL doesn't match some form of model you've got. Then you've got to verify, triage it, fix the issues, and go around continually measuring the coverage and go on and on and on and benchmark it. So it's a long process. Starts with finding the team, working out a plan, choosing the tools and capabilities, and then getting on with it. Right, so let's get on and look at the different approaches. So during this session, we're going to introducing different components like ISS and ISG, and I might talk about them as I go, or they'll be discussed in sections further on their own. So, hardware DV approaches for a RISC-V CPU. Listed down here, 6 real DV approaches and another one up front. And what I'm going to do now is talk through each one of these and give some examples of it as we go. Now, it's important to note that not all projects have the same requirements in terms of schedule or resources that they can throw at it or the verification needs. It depends what they're after. If it's a research project, there's absolutely no way you're going to put 5 people on it for a year to do it. Whereas if you want to sell the world's greatest application process, you're going to ARM run 10 to the 15 cycles on their processors, right? So you've got to choose, and each project will have different requirements of how much verification that they need. So let's first start Hello World as a DV approach. This approach is really where you get a program, you compile it up, you run it on your design, and it runs. And it's basically from the approach that, well, if I can get my program to run, then my design works, right? My DV's done. And if I can boot Linux on my processor, hey, my DV challenge is sorted. Well, that's not really the case. It really is just one path through the design, right? If you can get a program to run, that's fantastic. If you can get Linux to run on your core, that is a tremendous milestone. Don't get that wrong, but it's not DV. It's one program, one path thread. So this might be absolutely fine for test chips, for research and academic, for hobbies. It's fantastic if you can get something to run, but it's not for a commercial product. If you want to build commercial products, Hello World approach is not a DV approach. Yep, you need your HDL simulator, you need your FPGA, you need some silicon, sure, and a test harness, but don't get confused. Getting a program to run is not verification. Let's talk about the next one, self-checking tests. So this is where you basically have a program, some form of test bench, an RTL, or maybe it's an FPGA or something, and you get some data out of it. So you basically load up a program and run it. And it often will check its own results. So it'll do an addition and say, well, I should get this result in another register. And it maybe writes a bit into memory or writes a log. So it is checking its running. And if it prints a message to a log or to a bit in memory, it can then write that out to a file. So you can get maybe a signature file coming out of your design. And then you can run that on another implementation. So if you've got an RTL, you can have a reference simulator in there and you get a signature out, and then you can do a file compare. Okay, so you can compare the results. So you execute your design, you execute a reference, you get a file with a login saying I did this, I did that, and you can compare it. And actually, this is the approach done by RISC-V International on the compliance, the architectural validation test they do, where they basically write out a signature at the end of the execution, whether it's the design or whether it's on a reference simulator, and you get the signature and then you compare the signatures. So this is a simple approach to DV. You get data out of the design, and then after the simulation, you compare it. But often it is really just logs of I did this, I did that. And so it's basically very simple to do this. You need a basic ISS, and I put a link here to one. We as Imperas, we make something called RISC-V OVP Sim available as an ISS up on GitHub, so you can download it. It's free to use for both academic, personal, and commercial usages. And it's a free simulator, basically. We also put tool chains up there, which are based around GCC, pre-compiled. So again, you can just download and get those. So it's, this approach, this simple check, is a very simple approach to, you can get programs to run. It's very good for simple tests. You can get basic functionality working with it and feel some level of comfort. But you still need a very accurate reference model which will compare to what you're doing. So it's not a robust DV solution. It's really elementary DV. Let's look at the next one, post-simulation trace log file compare. So this is really entry-level DV, where you're going to get a program. So here, in this case, in this example, this was from used in the low-risk IBEX initially with the CHIPS Alliance organization with the open source cause, and working Google Cloud built this generator. I'll talk a little bit more about it later, an instruction stream generator. Actually, it writes out an assembler, not C file, which you then have to use a tool chain to turn it into a memory, an ELF file, a binary version. And then you run that program on your RTL, and you run it on a reference. And you do it by tracing all the instructions coming out. So it's a log file, not just of a few printf statements, but actually of instruction by instruction and register by register. You dump out a trace, and then you write a program to compare these traces and to try and keep them in sync. And at the end of the run, you run them to compare and see how that works. And again, we have a simulator, a more advanced one, which also we make available, RISC-V OVP Sim Plus, and it includes full trace and debug capabilities in there. And that is used actually in the Google Cloud RISC-V DV, which is a post-simulation trace compare technology. And in the Google generator, it basically generates the test and then runs one design and then the reference simulator and does a compare, and it does that in a large series of Python scripts in there to do that. And so this is sort of entry-level DV where you run the simulator with a trace, you run the design under test with a trace, and you compare them looking for differences. And actually note, this is not co-simulation. It says in the CHIPS Alliance slide it's co. It's not. You're running them sequentially. It's not a co-anything. And so, in summary, this sort of post-sim trace compare is it compares files after the runs. It can be signatures, it could be instruction trace, and you can use random instructions because you don't need to know the results because you're comparing with the reference. It's a comparison method, and usually this is the easiest method to implement in terms of DV, very simple DV, because you can capture the program flow and the data, because you can monitor the PC and the registers, and as long as the tracing format's right, it's not too hard to get up and running. You can potentially get an awful lot of files that you've got to manipulate, and they can be quite large. You can waste time because you obviously don't do the compare till you run the large simulations, and then you compare them. You don't know, it could be the 5th instruction that goes wrong. And it doesn't work at all well for asynchronous events where you've got interrupts, where you've got in the design under test a pipeline where things are doing things in different orders, and obviously your reference model is not going to be doing that type of stuff. So it can be very difficult. So traditionally this isn't used for any form of complex designs. Again, it's an entry-level approach. So it's not a real robust DV solution for commercial cores. And of course, you do need to get a reference, and we make some freely available references available. But if you've got your own design, you will need to get a reference model to compare against, which has any customization that you've put in there. So you'll have to get a reference model which matches your RTL. And at Imperas, we do that. Our models are always configurable and extendable like that. So we tend to work with people, and then we can make the simulators pretty freely available for them. So entry level, it's a good starting point to do verification in there. Okay, so now let's get into the more sophisticated ones. This is the first synchronous lockstep approach that's being used. We can see here I've listed the different companies and times that these have been used in there. And so this is actually first half of 2020. This was up and running in the open hardware group. So this is really what we call a sort of synchronous DV, synchronous lockstep, we've been working in the open hardware group on this for a couple of years here. And open hardware has a focus of building open source cores with high quality verification environments in them. And built this environment, it uses an Imperas reference model encapsulated in a SystemVerilog environment. It has uses the Google generator to generate tests for it, has functional coverage in there, comparison is in there. And initially in the sort of first generation in early 2020, it was very much a synchronous approach. So it's a tandem lockstep approach where you run both the reference and the design under test together, clock by clock effectively, and you're comparing them all the time. And it's not too complex to set up, but as long as there's no asynchronous stuff going on, you can be comparing the PC, you can be comparing the general purpose registers or the control and state registers in there, and other internal state instruction by instruction. You don't tend to have to save data, and you don't need to beforehand know what results you're going to get because you are comparing to a reference. So it works really well with the random generators and things. And the great thing is that when there's a mismatch, it tells you at the appropriate point in there. And so this was a very good solution, up and running in the open hardware world for one of the cores. And in summary, it's instruction by instruction lockstep. You're comparing the execution flow, you're comparing the program flow, you're comparing sort of internal states in there as well, and you get an immediate comparison. So it allows you to debug and introspect things at the point of failure, which is very, very powerful. So you don't waste a lot of execution cycles and have lots of files to trawl through. When it fails, you're there at the point and you can look into that. And it works very well for synchronous, and we'll talk about asynchronous in a minute. But it's not too hard to set up this synchronous environment, but it does require that your RTL design under test can provide the right information up from the design up to the the comparison that you need to do. So it's a lockstep approach. A lockstep compare approach is by far the best approach in there that you can do. And again, your reference model has to match your RTL, and so you have to make sure the reference model can be extended to be the same as the RTL. And in Imperas, if you're using Imperas models, we can configure that and set that up so that that works seamlessly, works properly there. So the fourth approach builds on the synchronous and is an asynchronous approach. It does all the synchronous stuff and the asynchronous. And this again was originally this is work. We can show this work done in the Open Hardware group in the second half of 2020. There, it's an asynchronous approach, and it really is a high quality DV approach. And then it builds on the synchronous and it adds asynchronous things in there. And you can see there's a bit more sophistication in the test bench here because you've got to think about the debug agents in there, interrupt agents, and actually in this case assertions have been added in there because you want to check things with interrupts that have happened at certain times and things like that. So it becomes a lot more sophisticated. So this is really a sort of second generation of a test bench that was evolved for this 40p core, which was basically signed off frozen at the end of 2020 with this, and that used the Imperas reference model wrapped in SystemVerilog in there. And so it's similar to the previous one, which was synchronous, but it adds the asynchronous. And you can add out of order in there, or multi-process, multi-heart in there, debug agents in there, interrupts, multi-issue can all be done with an asynchronous approach. But you do have to build some more components there to do with the tracing capability and the assertions and everything like that. So it's pretty hard to get a good asynchronous environment up and running. It's pretty complex and it's quite sort of expensive in terms of labor and details. And the biggest challenge is getting the data out of the RTL's pipeline, the processor's pipeline, in a way that can control the reference models and things like that. And we'll see how we've been evolving that in there. So in summary, it's instruction, this sort of level 4 here, this asynchronous is instruction by instruction lockstep, including the asynchronous stuff. You get an immediate comparison. So it's very powerful, so you can see when things go wrong, what's going on in there. You can handle hardware real-time effects, multi-core issues, out-of-order issues and things like that. But it is going to be quite hard to set up. And a key component of it is the RTL tracer, providing the right information out of the pipeline up into the test bench. We'll talk about that more with a standard interface that's evolving here. So it can be very expensive to get this up there, but it is the highest quality approach, and it is by far the best approach doing this lockstep for DV. Let's now talk about test benches using standards. First, we're going to have to digress into why we need standards. So moving forward, we have lots of challenges. We just saw the complexity of the the asynchronous test bench that was involved in Open Hardware at the end of 2020. And there's many components that are in there. Yep, there's the device under test and its encapsulation, and the tracer information to control the device under test. Then yes, there's the reference model and the configuration of that and all the other things with comparison and synchronization for synchronous and asynchronous operations. And then there's the functional coverage that you need to put in there. Then there's the test bench to control everything, and then there's the test. And each component actually has different interfaces and requirements on the interfaces. And it would be a complete disaster for RISC-V and process if every design team had to reinvent everything for each design. That would be so inefficient and so much work. So we need standard interfaces, and there are several blocks that do need these. And today they have different interfaces, and they're all ad hoc at the moment. And these components come from different suppliers and different developers, and probably used in different projects. And the thing is that if the standards exist, if there are standards, then verification IP can be created and licensed. And then you get benefits from that. You can reuse blocks. There's common ways to do things. You can start up things very quickly. You can be much more efficient. So there's lots of goals to why you need standards, and you need to be thinking about when you're developing standards. And if there are standards, why would you adopt them? Well, you have to have some interfaces, and they do not need to be proprietary. You don't need to have your own interface. You could use a standard interface and build your own technologies around. That's fine. And we're going to be talking about RVVI and what that is, RISC-V verification interface, and it's available on GitHub. And we'll talk about it and where it comes from, and because it's been used as it is for a while, and it's also been flushed out before, sort of previous version that we sort of evolved this from. And there really is no downside to its adoption. And the upside is you can potentially make use of other tools. And the types of tools that can be used, for example, is the reference models that, and Imperas has a solution in that area. Test bench components can be used in there, like functional coverage and assertion, log file writers, signature writers. There's several reasons why it would be good to adopt standards. So let's talk about the RISC-V verification interface. Well, it's evolved over the last 2 years. Some of the work in the open hardware group, but Imperas sort of with some of the customers that we've been working with on there, and several different RISC-V verification projects. And the open hardware group is building this sort of reusable Core 5 cores and trying to have a reusable test bench in there for these cores. And so that's sort of where this work has originally sort of come from and been used. And there was previously something called the formal interface, RISC-V formal interface, which was targeting formal tools, actually from a company called Symbiotics. And it really was to just observe information out of the cores so that the formal tools could try and make use of it. But for DV, you need a lot more than that's available in RVFI. And what's happened is people have tried to adopt RVFI for verification, but they end up just extending it with proprietary extensions, and that's not really the right approach. And what we did with RVVI is we took some of the capabilities out of RVFI and put those into the Verilog part of the RVVI interface. So you could think of it as a sort of a superset updated of it. So let's talk about RVVI here. So there are several components that we've talked about in here, and there are several areas which really do need interfaces. And there's two main components that we need to consider: the interface of the test bench to the core, and the interface of the test bench to the reference model. Now, if we look at this from a core point of view, you need to get two things out of there. You need to get the trace stuff from in terms of the data, but also the asynchronous stuff from the net and other sort of control things. So there's really two parts of this RVVI Verilog, the state stuff and the nets. And in its form, it provides a sort of streaming trace data, but also can handle multi-hop, multi-issue, out-of-order things. And there's a specification of this on a GitHub, RISC-V verification RVVI. Then the second half of it talks into the reference subsystem, which isn't just the reference model, it's a whole DV subsystem, and it controls it. And we're going to go through this in more detail. And the third area of RVVI, which is under a work in progress at the moment, is to do with the peripherals, the virtual components that need to live in the test bench to do things like generate interrupts, control the debug port, maybe to print messages to files or to consoles and things, and to have timers. And these need to be both available in a sort of SystemVerilog environment, but also in ISSs and C test benches in there. So there are several components as part of RVVI. And where they sit is that the RTL will need to build a tracer to get the information out, and that can make use of this RVVI Verilog, and the reference model and the reference subsystem can use it. And obviously, it needs to be in a Verilog environment, and obviously reference models tend to be in C and binaries of those, and so do DV subsystems. So it needs to have, if it's in C, the API needs to be available both with a C header, but also a Verilog header through the DPI, so it can be controlled in a Verilog test bench. And so there are several areas, main area onto the RTL on the left, and the reference subsystem on the right. So let's look at the 5 components now that we see in a standard test bench. The first is the design under test, the RTL, the core. It's a key component, and it's going to have some form of memory and interfaces and things sort of inside it. And a key component here is to get the data out of it into the test bench, but also there needs to be a control interface. And the quality of this tracer really does determine how many features you're going to have in your verification environment for it. And we talk about using RVVI, but it actually can be the interface out from the DUT out into the test bench can be bespoke or proprietary. But if you do that, you're not going to be able to make reuse. You need to reinvent everything all the time. So it's much better to make this a standard interface from the DUT up into the test bench. Second thing is this the tests and the stream generators. Obviously, they interface because there's a standard sort of ELF file or binary file that they'll be used. You're going to use tool chains like GCC or LLVM to get them up and running. Yes, you're going to have directed tests, and you might acquire those, or you're going to use a constrained random test generator. You could use a commercial one such as Valtrix, Sting, which I'll talk a little bit about later, I hope, if I get time, and also the Google instruction stream generator RISC-V DV, which is a SystemVerilog open source one. Just a little plug here for Imperas and tests. So when you're developing a CPU, you can never have enough tests. And initially working with the customer, we were contracted to do it, and we built a directed RISC-V test generator, which could generate tests. We built instruction coverage measuring VIP, which we include as part of our simulators. And also internally, we use a mutating fault simulator to test the quality of the tests that we build. And we generate these test suites targeting architectural compatibility. They're not full DV, but they check that you've really understood the specification, as in the same way that the RISC-V International Architectural Test Working Group have specified, and these match up to the coverage requirements that they have. And we currently provide over 50 free test suites covering 32 and 64-bit. Most of the subsets of the extensions there, from the maths, the floating point, the compress, bitmanip, crypto, SIMD, the vectors, and we provide those on GitHub, so you can download the information about those. And to get some of them, you have to register, but they are free and available as Apache. So you can't have enough tests. It's a good place to get some initial testing. In terms of functional coverage, normally functional coverage is written in SystemVerilog with cover groups and cover points and assertions. And what it's focusing on is you have a verification plan. You'll say these are the things we need to make sure we do. And the cover groups, cover points allows you to measure those. And from a RISC-V CPU test bench point of view, you can get functional coverage could sit on top of the tracer using the standard RVVI Verilog, and we have examples of this where you can get functional coverage from straight out of the RVVI interface. So all you have to do is build the interface out from your core, and you can get functional coverage there. And typically, functional coverage, it's going to be very, there's going to be sort of two paths to it. One is around the ISA and the standard parts of it for the measuring sort of standard extensions and things. Then there's going to be things specific to do with DV, for example, hazards where you've got sequentially, you're looking at which operands are used by which instructions in sequence. And then there's going to be things related to the privilege mode. And then there will be very specific things related to your specific pipeline and micro architecture. And typically these functional coverage systems are going to be written in SystemVerilog using cover groups and cover points. Central part is the test bench or harness. And this is the thing that instances and connects everything together. It controls the stepping of the instructions, and it connects things together between the device under test and the reference subsystem, which is doing the verification. And it will include connections for whatever synchronizing and comparing things. It will have some form of sort of virtual peripherals in it to do things like logging to the screen or to files. Probably has got some timers for doing asynchronous interrupts and things like that. And, you know, a test bench can be in SystemVerilog, or if you're using a C-based simulator, you know, it can be in C or C++. And we actually provide templates with our environment for both C and C++ and for SystemVerilog usage for CPU DV. And on the right of the previous pictures was the reference subsystem. So this is more than a reference model. It needs to have other technologies in there. So it's going to have the reference model. It's going to have some DV infrastructure, and also an interface into the test bench. And it's responsible, you know, for the DV subsystem is for the configuring the model, doing the comparisons, and the references state, so DUT to compare the two, and the synchronization and control. So let's drill down now into the reference model a little bit. RISC-V is highly configurable and extendable. And if you just take the standard, don't extend it with any proprietary extensions, there's hundreds of sort of questions you need to answer and set up whether this register's got this bit read-only or read-write, and all this has an effect on the reference to get it exactly right. So it can get a little complicated. So as an example of a reference model, in Imperas we provide what we call an envelope model, which is a full model of a full RISC-V specification. And it's high quality simulator used by many people using the compliance group, used for verification, used for test development. And it covers the whole standard, both all the existing current ratified stuff, but also future. So it has all the 32 and 64-bit versions. It has vectors, bit manip, and these are all the versions. And one of the key things about the Imperas model is you can select exactly which version that you want the model to represent, which is good because everybody's RTL isn't just the latest spec, because they will have been building it over the last year, and at that point the bit manip was down at version 0.93 and the crypto was maybe early, or the Cindy still isn't ratified yet, and maybe they only implement certain versions of these the standard. And so the Imperas model comes as a patch. It's used by a lot of different companies, and it's been used as the sort of golden reference model by many people in the verification of their RTL. One of the things that's key about RISC-V is that even though you can have it's a very sophisticated instruction set architecture with a lot of different extensions, you're allowed to add your own instructions and add your own state and registers in there. And in Imperas, we built a methodology around our sort of modeling capability. So we develop and maintain the base model, which is the standard, which is fully configurable, so you can select all the different versions and options that you might want in there. But we have a methodology and examples and templates and to show how you extend that. So you layer this on the side. So you don't change the original source. You could do, but it's not the right way from a maintenance point of view. So you can extend it in, and we provide templates and documentation on how you can extend that to add your own capabilities in there. So the whole thing about the Imperas technology, it represents the whole current standard, but it's architected to be easily extended and maintained. And we get a reference from people that are using our technology, very happy with it. I'll leave you to read that afterwards from the video. So now let's look at how these standards, how these verification, how these components are used in a real DV environment. And what we're going to do is drill down into an example based around commercial tools, but also with open source cores in there, and to drill down and walk through that in a detailed demonstration. It's going to be the Imperas DV is the name of the technology that we're going to drill down into. The basic test bench components in there, we're going to be talking about the Imperas DV, which is going to be on the right, the test bench, and then RISC-V core on the left, which is going to be the low risks IBEX. We're going to really focus on the DUT and the subsystem on the right and the tracer. We're not going to look at all the other components in there. So the Imperas DV, so it's a bit on the right in the other diagrams. It encapsulates the reference model, has technology so you can basically select the model, say which variant it is, configure it. It contains information about the state of the device under test. It has synchronization technology in it so that it can do all the asynchronous natures of multi-heart, multiple cores in there, whether it's got interrupts and debug and other things that are going on. It includes comparison technology. It has built-in instruction coverage, and it's completely configurable and traceable. It can be used in a SystemVerilog environment or a C++C environment. So it's a very simple to use technology with a lot of complexity under the hood, but it's very simple to adopt and use. The test bench harness will then sit to the left of that and connect to it. It will instance and connect everything together. It will control and step things. It will connect things from the device under test across into the the reference subsystem. And again, in the Imperas solution, it can be in SystemVerilog or it can be C or C++ in there. We provide, again, templates of the test bench of how it connects things together. We'd expect people to make use of those and extend it. When you put it together, you have the reference on the right, the DUT on the left, you have RVVI connecting the two things together. And when you set things up, you have to obviously set up the reference to be the same as the device under test, configure it. You need to select what you're trying to do in terms of what compare to do, what type of capabilities you're going to be using, what tracing and logging you're going to do, and whether you're going to do coverage in there and things, and other DV control options. And that's the type of things that you'll need to set up. So now what we're going to do is have a demonstration and see this Imperas DV in action and walk through that in detail. As I said, it's going to be Imperas DV. The core is the low-risk IBEX. The simulator is going to be SystemVerilog one, and we're going to go through synchronous lockstep-compare methodology. So we're going to show overview to recap on where we are, walk through some of the headers in there, look through some of the tracer code, walk through a SystemVerilog test bench and harness, run some examples, see how we deal with the fail and how we drill down into that, show a little bit of some of the architectural tests and social instruction coverage that comes out of it. So now I'm going to hand you over to Lee Moore of Imperas, who's going to spend the next 30 minutes and go through and walk through a detailed walkthrough of the Imperas DV and show RISC-V CPU verification in detail. Lee.
Thanks for the introduction, Simon. So what I'm going to do now is to run through a demonstration of Imperas DV in action on open source RISC cores. The core that we're going to do the demonstration on today is the IBEX core from LowRISC. The slide you're looking at here was actually shown earlier in the presentation, but I thought it would be worthwhile just taking a look at this again. For the main reason that this is put up on one of our GitHub sites, you'll find this under RISC-V verification RVVI. And this tries to describe the API semantics that are used in terms of communicating between the Imperas DV environment from an environment such as SystemVerilog, which is what we're going to use for this particular demonstration here. So you'll see there's a number of calls that are performed between the SystemVerilog domain and the domain of Imperas DV, and these are handled through SystemVerilog DPI. The calls themselves are generally prefixed with RVVI, and there's a number of different phases in which these calls are used. For example, what we've tried to show here is the breakup of things such as the initialization phase, then the loop phase where we're doing the comparisons while the program is executing. During the initialization phase, the kind of things that would be performed are instructing the Imperas DV environment information about the type of the target that we're intending to compare against. And in this case, as I already mentioned, it will be the low-risk IBEX core. And so within our library, we are able to configure a core to match whatever the specification of that core is. And we can communicate that through this RVVI interface when we perform the initialization routine. Once we're into the point where we're executing instructions on the RTL, then what we need to do is to pass information across to the Imperas DV environment, such as when instructions either retire or trap, and what the state of registers are at those points of execution. So the values in general purpose registers, the values in CSRs. And if you have a more complicated core, then values in vector registers or floating point registers, things like that. And so what happens is that as the execution progresses, that for each instruction that executes, information is passed across, and then we tell it to do a comparison with the reference that we're comparing against. At any point during this flow, if we get a difference, then it will report that back to us, and then we can go and investigate that accordingly. So what I've just showed there is the sort of calling sequence that we expect to be used, but it's also very important to be able to effectively describe the API so that it can be used within an environment such as System C or SystemVerilog, as we're shown in this example. And so what we also do is we provide a description in a Doxygen format of all of the calls that can be used to control the model. And these include a set of prologue functions, if you like, which is, you know, how you set up the environment prior to executing code. Then you have a set of calls which are used during the execution of the code, and you have a set of calls which are used during the comparison of the state between the two environments. But just to pull out a few simple ones, you know, there's a call to initialize the reference within the Imperas DV environment, and this would typically point to a predefined module within the library, such as in this case it's the IBEX core, the from low risk. But on top of that, you can then place extended parameters. So you can say, does it handle misaligned loads of stores? Which of the extension libraries are supported? So it's the model downstream that we use as part of the verification is highly configurable, not only from the standard set of specifications within the RISC-V organization's definition, but also for the custom extensions, be they CSRs or instructions. They can also be described as part of this environment and used as part of the entire verification flow. So as you can see we've got a very rich set of primitives here that can be called directly. In addition to this, what I'm going to show you in a moment is that we have a set of Verilog clients that watch the transactions on the RVVI interface itself and can drive this directly. What I want to do now is go and have a look at the code within the environment. So I already have this loaded into Eclipse. I mentioned earlier with the doxygenated format of the API, where we described the usage of the API calls, and here we see the header file that corresponds to the doxygenated format. So this is the interface into the Imperas DV product. And what we also do is we have a set of import DPI routines so that we can call those same functions from within a SystemVerilog environment, which is what I'm going to be showing here today. So for each of those API calls with the C header file, then we have the equivalent here that is used within the DPI. Now the API is part of this to actually control the communication with Imperas DV itself, but we also have this SystemVerilog interface, which is how the transactions are described to this part, to the later part of the system, and this is used in order to deconstruct the information that's coming from the RTL. And this is based upon some earlier technology that was developed, and it's been enhanced for usage within environments which are multi-heart, multi-issue. And so what you see is that for each of the individual parameters, sorry, individual wires within this interface, you'll notice that they are dimensioned by the number of hearts and the number of issues of each of those hearts themselves. So if we had something like a heart within a processor core which could perform 3 issues in parallel, then we can describe that in this format here. The intent here is to describe the flow of the program as it executes and communicate out the values of the program counter, the values in the X registers, whether the instructions continue to execute to retirement or whether they cause traps, updating CSRs and things like that. And pretty much we have everything contained within this interface, and so this has to be driven by part of the RTL code itself, sometimes via the test bench, in order to tell it how each of these signals are behaving as the program executes. And so if I was to look at an example of this, let's have a look at the IBEX top here. So the IBEX top level SystemVerilog contains an RVFI interface. So RVFI was a technology developed a couple of years ago, and it describes some of the capabilities regarding the GPRs that get written on instruction retirements. It also contains information about the order of the instructions as they execute, and also contains information about when instructions undergo an exception condition. And so what we can do is we can use that information to drive into this RVVI interface. You'll see here I instantiate this this component here, which is our RVVI interface, and we define the number of hearts and the number of issues for the processor that we're interested in using as part of the verification. It just so happens for this one, it's a single heart, single issue processor. And so that actually dimensions the content of this interface as we see here. So we can drive them directly by saying indexing in for heart 0 and issue 0 for each of these signals that are already coming out of this core. In addition, we can drive the general purpose register values as well. And what this means is now we've got a nice construction of data as the RTL is executing any instructions. This allows us then to produce what we term as a client to monitor this interface. So for example, here we have what's called our Verilog to API client, and this Verilog to API client will get instantiated. In fact, here you see the instantiation. So this is the instantiation of our Verilog to API client here. And inside of this client, what happens is it watches the transactions onto that bus, captures the information contained within them, and passes them on to the Imperas DV environment using the RVVI API routines that I showed earlier. So just to pull out a few simple ones, whenever we see a GPR value being set, then we have a function inside of this client which calls the RVVI DUT GPR set with the corresponding information for the given heart and the given register index and the given register index value. So that passes it automatically across for evaluation later when we tell the reference within the Imperas DV environment to say, okay, we've just executed an instruction or a sequence of instructions here. Please do the same on your side and tell us whether or not we have a difference in terms of the computation and the internal state at the end of the retirement. We have a similar routine that does some logging as well, and I'll be showing these as we run the demos. This is simply taking the stream of writes into the RVVI interface and producing a stream of logged messages telling us what's executing on each of the hearts, and when we have multiple issues, you know, where those issues are occurring on which hearts, things like that. Now at the top level, so we have our top level of our instance here, but then we have our test bench that instantiates this as well. And in our test bench, what we're actually doing here is we're controlling the setup and the execution of the RTL, passing the information across to Imperas DV, and then doing the comparisons and making sure that the state remains consistent. And if you remember, I said there's a number of phases. You know, you can consider this kind of like a prologue phase where we do the setup, then we have the execution phase where we're running through the instructions, and then there's an epilogue, which is where we write out any statistics. But also during that execution phase, you would expect to be applying effectively the assertions of ensuring that the environment is making sure that the state is correct and equivalent in both representations of the execution of the application. So if we were to look in here, we have this top level task called test bench control loop, and in here the first thing we do is we make sure there's a version check on the API. Assuming that's okay, then what we do is we initialize the reference model within Imperas DV in order to make it match the target of the processor that the processor RTL that we're intending to compare against. And so you'll see here we're configuring it as an RV32 supporting both the integer set and the compressed instruction set. Interestingly, there are a number of other parameters that can be set at runtime as well, and I'll go through some of that, and you can use this to layer on top additional capabilities that are available but switched at runtime. So we've worked with many groups that developed RTL, and an example of this would be the Open Hardware group, and they have some switches that configure the RTL, such as including or excluding the pulp instruction set. And so what you can do is you can configure this at runtime as well for the reference model that's being used for the comparison. The next thing is part of the setup. So there are some things we need to do in terms of describing the volatility of the RTL versus the reference model. There are some features within the RTL which can never be calculated in an architectural reference model. A good example of that is the cycle counter. The cycle counter cannot be calculated. It's usually based upon a clock, and therefore, because we don't have a clocked representation in an architectural model, that is something we define as volatile. Now, volatile doesn't mean that it's ignored or anything, because you have to use this information. Because if you imagine you have a piece of code that executes a branch on the value inside of one of these volatile registers, then you have to ensure that that branch takes the correct flow of control based upon the value in that volatile register. So there are some things we do to ensure that registers marked as volatile are passed across from the RTL to the reference model to ensure that execution of programs maintains consistent in both of those domains. And then after the setup, we go through the phase where we're executing the program that's running on both of these representations. And in the background, if you remember, because we're driving this RVVI interface, then all these API calls are being made across to the Imperas DV environment, performing sets and comparisons in the reference environment. And so if there are any failures during that period, they would actually be flagged, as we're executing across the code inside of here, inside of this forever loop. And then finally, as I mentioned, we have an epilogue phase, which is we would go through a shutdown phase. And during the shutdown phase, we would do things such as writing out statistics of number of comparisons, number of sets, and where we've had any miscompares at that point. A quick recap then before we go into the demonstration itself. So what I've described so far are the API routines that we have as part of Imperas DV. We have the interface, which we call RVVI, which is used to capture information being generated within the RTL and test bench and pass it on to the Imperas DV environment. And then we have the semantics of the operation, which is there's a prologue phase which sets up the environment. We have an execution and comparison phase whilst we're executing the code. And then we have the epilogue phase, which is where we would write out any statistics. So now let's show this in action. And what we're going to do here, I'm just going to flip across to my demonstration area. The first thing I'm going to show, I've got this all scripted up, by the way, because it makes it a lot easier to actually run things. I'm going to show running one of the compliance tests on the IBEX core RTL and being compared and controlled within the Imperas DV environment. And this is the add test that we're going to run here. So let's just run that. I'm actually running this under a commercial Verilog simulator. So we go through the compilation elaboration phase and then we go through the execution phase. So here's the interesting part here. There's not a lot to show because, of course, this is working perfectly fine. And in fact, all that happens is when we execute that program is that we get a summary telling us that we've performed a number of assignments or sets, which is where the API has, the client watching the RVVI interface has controlled the API to set information in the Imperas DV environment, and then it's done a number of comparisons. So here we see we've had on the PC 200 sets, 200 compares. The instruction bit pattern, when we perform a fetch, we've got 200 sets, 200 compares, and on the GPRs, then we have 200 sets and 6,400 comparisons. The reason why we have 6,400 comparisons here is because, of course, there are 32 GPRs, and not only do we check for GPRs that get set, we also look for side effects for ones that we ensure have not been set. So ultimately running this, it tells us we have 6,800 comparisons and we've had no difference. So I sometimes liken this environment to what we have here as to having a very smart assertion checker in your code, that in general, you expect it to be silent, but when something goes wrong, you want it to raise a flag and tell you that there's a problem. And so this is kind of like the silent scenario that we're watching here, that it's running in the background, it's doing lots and lots of checking, but it has nothing to tell us right now because there are no differences inside of this environment. So what we're going to do next is we're going to introduce a bug into the RTL. And so where I'm going to do this is in the ALU. You'll see here in this ALU, we put in a hash define or a tick define in terms of Verilog speak for something to corrupt the behavior of the ALU add in the ALU sub function. And what we can do is we can enable or disable this through our command line to exclude this bit of the code. Now, of course, the example I have here is running the ALU compliance test. So if I introduce a corruption here, I'm pretty hopeful that the compliance test should find this. So let's just have a look at the script that we're going to run here. So as I mentioned, we've got this tick define that's going to be enabled. And if I now run this, let's see what happens at this point. So again, we go through the elaboration phase. I've actually got this configured at the moment to tolerate 5 miscompares, and this is programmatic. We can say how many we want it to absorb before it goes through to a bailout condition. And what it tells us here is that at this program counter where we've executed an instruction, which is D8, we've got a miscompare. It's telling us that the device under test told us that the value of the X5 register was 0, and the value of the X5 register in our reference model under Imperas DV was D8. Because we've got the miscompare throttle to 5, then the program does actually continue executing, but of course this is continually reported. And then what we see is a further miscompare at this point, where we also have a miscompare in X10. Now, the first thing I would mention about this is that unfortunately we don't really have a lot of information here regarding the flow of execution that led up to this point where we saw the difference. And this is now where we start to get into the details of how we extract more information whenever we get problems with the state comparison between the RTL and the DUT, the RTL DUT and the Imperas DV environment. So the first thing I'm going to do here is to turn on some additional tracing. Again, it's actually scripted up here. And what I'm going to do is I'm going to turn on the tracing of the reference environment. And I'm going to, and if you recall earlier, I said that there are a number of things that we can control at runtime. There's a number of things we can control at compile time of the processor reference that we're using. So here's an example of where we're doing some controlling of the runtime side of things. So we're telling it to do some additional tracing, trace changed registers, give us an instruction count, tell us about modes if it's switching. It just so happens in this one actually it only runs in machine mode, but if we had a more complex core, then it would tell us about mode switches as well. So let's run this again. So it's still got the RTL fault in there. We're going to execute and see what additional tracing we get out. So you'll see here, this is the tracing now coming from Imperas DV, and it tells us at this point here we're executing an AUIPC instruction, and an AUIPC basically says add unsigned immediate to the program counter, and the unsigned immediate is 0. Therefore, we're just going to write the program counter into register X5. And yep, great, it tells us we've got D8 in the register X5. Unfortunately, the RTL tells us that it has 0, and this is why we had that difference at that point. And so if we continue executing, remember I said that X10 also has a fault in it, and so here we see an X10 failure because at this point here we've done an add immediate targeting X10, and again the RTL is saying that it has the value 0 in X10. Now let's turn on some further tracing. So what I also want to do is turn on some tracing from the RVVI interface. Remember I said that there are clients that we attach onto the RVVI. One of them is controlling the Imperas DV API calls. And we have another one which we call the VLG to log, which is watching the transactions and can log those transactions out based upon what is occurring on that RVVI interface. So let's let's run that now. So now we're going to have some logging of the interface itself and of our reference model. So this is actually more interesting now. So what do we get? So if I start at the beginning and then we can see the flow here. The first thing is that, so this is a message that's coming out of the logging of the RVVI interface. It tells us that an instruction was retired on heart 0. Its order was 1, so it's the first instruction, and it tells us the address of that instruction, it tells us the bit pattern of that instruction, and it tells us the disassembly of that instruction. And it also tells us that there were no register updates associated with that instruction, which is what we would expect, because there is no change at that point. The next instruction to be executed is a CSR read into the from the heart ID into X10, and so it reports that we've got a change on X10. It just so happens that that's a write, and I think it's and so it's writing in the value 0. And when we do the same operation on on our model, it compares because the default value is 0 at that point. Now, where we get the difference is more interesting. So if we extend out the difference here. So we see that the RVVI is reporting that it's retired an instruction, which is our AUIPC, but it's telling us that register X5 has the value 0, whereas the reference model has told us that it should have the value D8, and this is where we get our difference. So now we know exactly why we have a divergence between our design and the test, for the RTL for this, and we have a different value calculated in the reference environment. Now, there should be no surprise here, right? Because we've introduced a bug into the RTL. So, of course, the next thing we would want to do at this point is to take that bug away. So, what I'm going to do here, let's have a look at the next script. In fact, no, I'm not going to run that right now. What I'm going to do first of all is I'm going to modify our existing script, and I'm going to turn the error off. And I just want to show that now what we should get is an execution to the end with no differences, because there we go, that's perfect. So now we see, as we had before, except we've still got the tracing turned on. That's the important thing to note here. So when we ran the first example, all we got was the summary at the end, whereas now, in addition to the summary at the end, because we've got the tracing of both the RVVI interface and the tracing of the reference implementation, then we've got a lot more information at this point here. Of course, sometimes the problems that we have to investigate are far more complex than this, and can't simply be resolved by looking at traces, and we have to go into a mode where we do some interactive debug. And so what I want to move on to now is just showing how these tools and these technologies can help even during interactive debug. The first thing I'm going to show is adding some debug from the perspective of the SystemVerilog domain. So again, I've got a script set up here. So what this is going to do is it's going to run up a Verilog waveform viewer, and we can take a look at the content of the RVVI interface that is being driven from our model, from the RTL model, that is. I've already pre-selected some of the signals here to make this a bit quicker as far as demonstration is concerned. But the important thing to note is I've gone back to the point where we've got the bug inserted in the RTL, and so we see after 5 miscompares that we're going to perform a finish of the simulation at this point. And this is a cut down set of signals within the interface. It's really the only ones we're interested in looking at, because as I mentioned before, the IBEX core only supports GPR registers. There's no vectors or anything like that in here. But what we can do is we can push down and look at a lot of information and determine what's going on. So if I look at, first of all, the instructions themselves, here I see the instruction bit patterns that are being applied to the bus to the interface as we're executing our code. I can see the program counter. Let's move that up there. I can see the program counter value as well for those instructions that are being executed. So we know here that the first fetch occurs at address 80 on the IBEX core. And then in addition to that, we can see the transitions of, for example, the order, which is effectively the count. That should be really represented as a, let's change the radix. That should really be a decimal, so let's change that to decimal. So here we see the instructions in terms of their order definition as part of the RVVI interface. And then we see the individual registers on our heart 0 for issue 0 of all of the GPRs 0 through to 31. But as we've already discussed, that there are no changes to these registers as we're executing because of the problem we have already investigated here. Because of the environment we're working in here, we have access to a greater set of tools. We don't have access purely just to the SystemVerilog tools, because we also have the tools that come from the Imperas DV environment, and so we have interactive software debuggers on that side. And so what I can show here is running the interactive software debugger alternately to, or actually complementary to, running a waveform debugger as well. So we'll do the same thing here. Let's run up, we'll actually run up both. We can do this, and let's start the execution of the SystemVerilog simulation environment. If you recall, I mentioned earlier that we kind of act as a slave to SystemVerilog, and therefore we have to start the SystemVerilog simulation running. But once it's executing, we can take over control within our debug environment here. So I can step through the code, I can view registers. So if I open up my registers here, if I start stepping through the code, we can see that these will eventually get updated. There we go, we see an update of a register there. Interestingly, if I go back to my console here, it's going to report to me, same as before, telling me that we've got miscompares with the RTL at this point, because the add function is not working inside of the RTL. But the nice thing about this environment here is that you have complete visibility of everything as far as the reference is concerned. So you have the software view of the registers as they appear on the stack, assuming that they're conforming to some kind of ABI. And you also have visibility of the registers as they would appear in their physical hardware form in this window here as well. So if I was running a more complex program here, it just so happens that the compliance tests are written in assembler, but if I was running a high-level C program and I had a deeply nested stack, as I moved up and down the stack here, what you would notice is that the software registers, of course, would change context and value based upon where they were in that software stack, whereas of course the hardware registers would remain the same. So you're able to contextualize these two against each other. And we have, a full software debugger here that allows us to go and look at the code that's executing. We can look at the source code if there was, source code rather than assembler in here. And we can also go and look at all of the internals, including, not only the core registers, but things like the machine control state registers and recording information such as internally held state for what mode we're operating in or what the last exception was that occurred. I'm just going to shut all these windows down now and go back to where we were originally. And the last script I have here is pretty much similar to what we started off with the tracing turned on. I'm just going to run that just to see this again run through to the end with all the tracing. And so what that actually done there, just to show, we've actually turned off the RTL error. So we're not seeing the differences in terms of the add instructions misbehaving inside of the RTL code that we're executing. So hopefully that's given a good introduction as to how we can describe and communicate across to Imperas DV the operation of our device under test. So just to clarify and recap on this, so the way we do this is that we have a rich API in order to control and inform Imperas DV, and we use that by communicating data across the RVVI interface. And then on top of this, we have a set of comparison checks which tell us whenever there's a difference between the RTL and the Imperas DV environment. And when we have those, we have the capabilities of being able to perform additional tracing and interactive interrogation to see why those differences occur. So we can quite quickly narrow down the problems and determine the correct resolution to why we're getting incorrect or non-intended behavior in terms of the RTL versus R reference. The last part of the demonstration I want to show here is some of the built-in coverage capabilities we have with the Imperas DV product. The first thing I'm going to do is I'm going to rerun the first example. If you recall, this was simply running the compliance test for the add instruction. So let's just set that one off again. And in the background, I'm actually generating some coverage, as you can see here. I haven't highlighted this before, but we're capturing coverage as we run this. And if we look at the coverage report for running that test, what we see is this is broken down into individual tests and then cross coverage between source and destination registers and an accumulation at the bottom, which I'll show you. So if we look here, so we've got some cross coverage of RS1 and RS2 input operands, and we've got some coverage for the individual destination and source registers. So this particular test that was written by the compliance group has pretty much targeted all of the combinations. As you can see, they're all hitting 100%. But more interestingly, if we go down this file now, we'll notice that we start to hit some zeros. And this is because these instructions are not being targeted by this test. This is a specific test to exercise the add instruction in the I extension of the subset. And we get a summary at the bottom telling us that we've exercised and counted so many instructions, and tells us how many unique instructions and how many coverage points we've actually hit. Now what I can do is I've actually got a number of tests here. I think there are 5 tests, and I can run all of those tests. So let me do that. I've got a script here that's going to run all 5 tests. Where is that? Okay, there we go. And this is going to generate coverage reports for each individual test as it executes. But more interestingly, what it's going to do is it's going to also collate all of those and aggregate them into a single report, and we can extract that information and take a look. So we see here for this last test that ran, which was I'm not sure which one it was actually, but importantly here we see the 5 tests that we've aggregated. And this is the add, the and, branch if less than, load word, store word. And you can see here we've hit this many coverage points, so 503 out of 2,540 coverage points. In fact, let's do this, if I grep for this description here in all of the coverage files, excellent. That's what I would hope to see. So we can see that each individual test has a smaller amount of coverage than the overall amalgamation of those. So as we can see here, the add and the and are producing less than 10%, just slightly less than 10%, and the others are 7 and 6%. But when they're added together in this collated report here, then we see that we're hitting 500 of the coverage points. And obviously, as we add more tests into this set of tests, then when we generate the collated report, we'd start to see that our coverage improves overall. Hopefully this has given a good introduction into the work we've been doing with the Imperas DV capabilities for design verification of RTL RISC-V based processors. What I'll do now is I'll pass back to Simon, and any questions we can also address later on. Thanks a lot.
Yes, thank you, Lee, for that demonstration of Imperas DV with the low-risk IBEX core using a SystemVerilog simulator. And what you showed there was the synchronous lockstep compare, where we looked through the different things on the RVVI. We looked at the APIs in there. We looked through a little bit of the connection of the tracer there, a bit about the harness, and then we saw some runs and passes and a bail and some instruction coverage. So thank you very much for that demo, Lee. We're now going to continue and talk about the other components that we see in the typical CPU DV environment. There are four areas and technology components that we're going to talk about. We're going to talk about tests and test suites and the compliance. We're going to talk about instruction stream generators. We're going to talk about functional coverage, both Imperas built-in technology and also SystemVerilog functional coverage. And then we're going to finish up really with instruction set simulators. So now let's get on and talk about compliance. So RISC-V International has been working on compliance testing since 2018, and the status today is that the test suites, basic unprivileged and older extensions, ratified extensions are available, and it's a simple framework for running the device under test and provides a signature so you can compare. And they're working on a new framework to run in a post-simulation signature compare mode where the SAIL formal model is encapsulated and has been configured by YAML, and they don't provide reference signatures going forward, so it's dynamic on the fly signature generation. So you've got to be able to run the SAIL model and all this sort of stuff. And the process is self-certification, so you run the tests on your device, and then obviously if they pass, you declare that it's compliant. The charter of the group is really it's an umbrella group in RISC-V to provide guidance and strategy and oversight of the development of the tests. And it really provides this guidance for the groups working on the extensions, and they'll be developing the tests for this. You have to be a member of RISC-V International to join and participate in things like the working group. And there is a mailing list to keep people up to date on it with about 100 and something members. It does have a GitHub, and so you don't have to be a member to access the tests. You can download them from the GitHub there. And if you look in here, you can see the different sort of groupings of extensions here. For example, the 32IM for the machine mode 32-bit XLAN. If I click on that, we can see that we have the individual test directories, for example, the integer, the floating point, the compressed, the maths. Now, when verifying a design, you can never have enough tests. I'm now going to spend a bit of time talking about the Imperas test suites. Now, we built internally a directed RISC-V test generator, actually on a customer contract to do that, to generate some tests for them. And we also have some instruction coverage measuring verification IP, and we have an internal mutating fault simulator for qualifying and testing the test to see the quality of them. So that's a mutating fault simulator, that's an internal technology. And we generate these test suites for targeting architectural compatibility as defined by RISC-V International, the working group on coverage, as I mentioned there. And we've generated over 50 test suites that we make available. We make available with our RISC-V OVP Sim-free simulator on the GitHub, and we have one of the testers there, and the others are on the OVP World website, and there's a link there on the screen, and you can go there and download them from the GitHub and also from OVP World. I'm now going to walk you through the GitHub and show some running. So I'm now looking at the GitHub here, and we can see on here we've got it's at RISC-V OVP and Imperas RISC-V tests. Obviously, there's a README which explains it. There's the simulators. We can see in terms of targets, we have target both the Imperas free simulators and also the RISC-V International's formal model that we have as targets to test these with. And the main thing really is the test suites. If we go to the test suites, we're separated by machine mode at the moment. We've not released any of our privilege mode tests that we're working on those at the moment. We can see the tests here. there's some 50 different tests that are available here under Apache as open source that you can download. Some of them here and some from our OVP World website. And we list, the number of files that are part of the test suite, how many instructions they're targeting, and what the number of instructions there are in the test, and basically the coverage achieved, and then the subset of them. And you can see here, some of them. So for the integer stuff, there's 48 different test files, 48 different instructions that were tested. For the floating point, there's actually, for the vectors, there's a whole bunch. In some of them, there's 1,400 tests in there. So there's quite a lot of testing, some 250 instructions. We go through all of the bit manip, the ZB ones, the crypto, the K ones, and we've also got in here things like the newer ones, MMUL in there, which is a subset. And we also have the DSP ones where there's a lot of different 300 odd instructions in there. So there's some 50 different test suites that you can go and download and get access to for free as tests. And if we were to just look at one of these, if we look at the integer ones, we have in here the basic source of it, so we can actually see the source, which we'll have to assemble up, and it's all done with macros passing it in. And it also says what results it's expecting in there. And with the Imperas test, there's actually assertions to check the results are what we expect. We also provide references in there, so there's the signature because it is a post-simulation signature compare methodology. And for each test, we provide several files giving you information about it. For example, there's the coverage of it, so you can see what is actually covered by that test. So you can see here for the basic 32i, there's actually only a couple of bits of instructions. One instruction, WFI, we don't test here in this suite, which is part of that set, and also sort of branch instructions which branch to themselves are not easy to test in a simple mechanism like this. We also provide details of the test, so it tells you what group the instructions are in, how many of each are actually used in that group, and if there are any instructions used from other groups. For example, here we obviously have to set up some CSRs so that are in there. And we also provide some information about the sizes to show how big each test is. So having looked at that on the GitHub, which you can download, I've now got on my Linux machine here, so we can actually have a look at it. So I've downloaded from the GitHub the test directory, and we can see from the changelog file here, what the current versions are that are supported by the different tests that are in it. And then we've got it's a simple make and bash mechanism in the same way as the existing RISC-V compliance tests in there. And you basically say you make what you're going to make file that drives it. So you say what device you're trying to do. I want to simulate, verify, and cover, and I can run that. Look, and we can see that it's actually gone through, compiled things up, simulated them and everything in there, and got the coverage we can expect. And actually, I can just have a look here at, we can look at the coverage file, and in here we can see that the logs of the different things that are in there. So we can actually just have a look at the overall coverage in there, so we can see the coverage for the full test. As we showed on the website, we provide these files on the website so that you can see that. So that's really a summary of the Imperas test, the architectural test that you can get. As I said, they're a free resource available from the GitHub, and when you register on OVP World, you can download them. They're available as source. You need a tool chain. We also provide a tool chain on the GitHub as well that you can download and get. So those are a good resource to use for some initial testing. As I said, you can't have enough tests. The university and a group from Bremen in Germany has been doing this, and what they basically said is that handwritten tests are good from a compliance point of view, but actually that's testing the positive. But what they were interested in, what negative testing, and to check that things and how they responded under the wrong instructions and things. And so what they did a lot of testing there. And what I've done is, I'm not going to run them here because there's an awful lot of tests. There's 8,000 tests in their sort of specification tests, which we've been using here. And when we run those through the coverage, through the simulation, obviously this is them passing, and they pass all the references they have. They test almost all the instructions in the instruction set, and extremely high quality. And if we were to actually just look and see the basic coverage of what oh, what they've got. Okay, so I haven't got that file there. I've already deleted it. So we could have a look and see that it actually is very few of the instructions are actually missed. And actually, here's the list of the coverage points that were missed. So obviously, branch to self you can't test easily, and e-break. So very few points are missed. That's extremely high quality testing from, and these are automatically generated, and there's a lot of those, there's 8,000. And then they have their fuzz test, which is trying to find out what's wrong with a model in terms of how it behaves in the illegal conditions. So this is good for the RTL or good for a model. So they've got some 13,000 tests in there. And when they run, yeah, it doesn't cover all the instructions. It's not aiming for coverage because it's testing for illegal conditions. And the interesting thing is when they did that, they didn't have access to a lot of RTL, but what they had is access, obviously, to reference models, simulator models. So they used as a reference our simulator RISC-V OVP sim for this. And this is a paper they presented actually at DAC, at the Design Automation Conference this year. And then they tested against the Spike and their own virtual platform simulator to Sail and GRIF formal models. And they found several bugs and issues and crashes and things with each of these models here. So these are a really good bunch of tests. And so there's some 8,000 of the spec tests, and in this lot there's some 13,000. So there's some 20,000 tests for this, and we're going to be putting them into our Imperas test suites that are going to be available, so that they're available for everybody to be able to use.
Having looked at test and compliance tests and different test suites, let's now move on to one of the other components in DV environments, instruction stream generators. We're going to look at three. We're going to talk about the Google one, then show some of the Force RISC-V running, and then Valtrex. So if we remember, in terms of the test bench components, the thing that we're going to be talking about now in this section is the instruction stream generator, which basically generates tests. Now, we're talking around here going to be showing and talking about an open source one from Google, and it's a UVM based one in this case. And what you do is you have to specify the device that you're dealing with, the device under test in terms of configurations. You target the instructions that you're trying to generate. You say what you're trying to do. You have to configure the reference model that you're going to be using for obviously comparisons. You obviously need to choose what tests you want to try and create. You can configure the test list, set some constraints for the randomization, and the output is you then get some tests. So let's now look at the Google Cloud one. So this is actually from a presentation that they did back in one of the earlier RISC-V summits. And the focus that they were doing, this is when they talked and announced it, was there needs to be several key features in a test generator. It's got to be randomized, where you randomize everything to do with instructions, the ordering, the program, the privilege mode. You have to be aware of the architectures. So you're trying to push tests into the corner cases. And it's got to be scalable to generate large programs if you want, and it needs to be extendable so that you can add your own instructions and things if you want. In terms of randomness, there are several types of randomness that you need to consider. Simple randomness from things like the operands and values and things, but also you want sequential randomness to make sure you've got different orders of instructions, so you can be triggering sort of dependencies in your pipelines and things. And then you need program level randomization to do with privilege modes and stuff around virtual memory, page table walking and things like that. Now, we worked with Google on this back to 1920 with Metrics as a simulator, and we basically developed a sort of a post-simulation trace compare around RISC-V OVP sim simulator. They were using that as the reference in there so that we would get a log out of it, and then we had to sort of process the trace file into a format that can be compared with the same as one that was coming out of the RTL. And there's and this is an actively maintained open source project, and there's a link there to the Google GitHub to download and use it. So now, having looked at that, let's move on and look at the another open source offering from the Open Hardware Group.
Of course, RISC-V was developed initially by FutureWay. It's open source, it's in C++, and there's a GitHub on open hardware. The initial focus was on RV64, but recently there's been work on the RV32, but it's not yet a key part of the open hardware flow for the open hardware cores. And now I'm going to talk about a third test generator, which is a commercial solution. A company called Valtrix, their product Sting, and this is a commercial product. And it's an extremely fast test generator, which generates code that runs on your device under test, and it's like portable stimulus. And it actually, one of the things that's very interesting, and that's the website for it, one of the things that's very interesting is that yes, it's constrained random, but it's also graph based. So it allows you to do direct sequences and then drive those with constrained random, or have random sequences driven by directed. So it's very interesting in that way, and it gives you a lot of control over the tests that are generated. So if I just run this, I'm not going to run the generator, I don't have it here. What I do have is some of the ELF files that it's generated, and I can just, I've just generated a script which just runs them. It runs them through the simulators, so we can see that it runs, and it's so it runs. Each test is sort of 10 to 20,000 instructions, and out of the 210 instructions we're looking at, it's covered a lot of them, which is pretty good. And we've actually, this was running the, what is it? It's a 64-bit, so it's running 64-bit IMC, also the CSRs and the FENSI instruction. And then actually, in this case, it was running all the bit manipulation stuff as well. So very powerful, very fast test generator. It gets very good coverage. Another component of the RISC-V processor DV environment is functional coverage, and that's what we're going to talk about now. There's two types of coverage I'm going to talk about. First is the Imperas built-in instruction coverage, and then some SystemVerilog functional coverage. So Imperas instruction coverage, so it's built in actually as an extension library to the Imperas models and simulators. So it works with all of the simulators, including the free RISC-V OVP Sim Plus, which we've shown, and actually I'll show you again in a minute. And the focus of the Imperas built-in instruction coverage is for the architectural validation test, for the measurement of basic architectural operations. It's really not intended for hardware DV testing, which will be a lot more sophisticated than what we've built in, and it will be normally specific to the pipeline of the processor that you're building there. And the built-in coverage is controlled by command line, so you tailor the options for each run, you get some output, and after you've done the individual runs, you can collate it into a sort of measured coverage for the whole suite, and that shows what has and has not been covered, and you can choose the different things that you're trying to cover in there. Now, earlier we showed the Imperas DV technology, and you may have noticed that down there on the right is the sort of built-in instruction coverage. And so it's built in, as I said, into the simulators model, so it's available in the Imperas DV instruction coverage. I'm now going to show you some of it. So let's have a look at Imperas built-in instruction coverage. So I'm going to do this by looking at the RISC-V OVPs and Imperas tests GitHub, so we can see it from there. And in there we'll see, we saw that earlier with the Imperas tests. And if we look at the reference menu, we can go in here and see the in the documentation directory the RISC-V OVP Sim manual. So if we have a look at that, it's a user guide explained. It's got a section on instruction function coverage that's built in. And we can see, obviously, RISC-V OVP Sim Plus is an executable. And what we can see that several different options for it. We can see what the options are by typing help. One of them is that you can have the extensions. So there we can see with IMC, we can say which variant we're targeting and the ELF file from it. And we'll see reports showing what the results are there for it. So it's very simple to actually use. We can choose the coverage type, we can choose what we're focusing on, the arguments, the extensions or instructions. And we'll see what instructions are seen, what operands are hit, and some cross coverage and stuff. We can look at the more extended coverage and see comparison of values and also some of the min-max stuff that we can see from it.
and we can accumulate as we showed from the runs in there. We can say when we want coverage to start, so we can ignore startup and shutdown. We can include pseudo instructions or not. And so it's quite sophisticated in there. So if I now just go back here to the test suite and have a look at some of the output. So if we look in the test suites, we can see here we provide coverage reports in there so that we've generated with our tool. So we can see, basic coverage, as we said, for each instruction, we can see the operands and see whether we've seen them and how many times. And at the end, we'll actually see which ones we didn't hit. And obviously for the 32 IDs, there's only one instruction we didn't hit and a few of the actual cover points were missed in here. So it's quite easy to use, easy to set up, and it's built into the Imperas simulator products to use. Having looked at the Imperas built-in coverage, now we're going to look at the SystemVerilog coverage. Now, when we were talking about the Imperas DB and the test bench, we can see that there is out of the core, there needs to be some form of tracing technology, and then there can be functional coverage connected to that. And that's going to measure what the architecture and the microarchitecture is actually doing. Now, we saw earlier in the video, the demonstration that we did, that in the presentation, that of the Imperas DV, that there are connections from the tracer out to the test harness to do with the logging and to do with the APIs through RVVI, through its Verilog interface in it. And what that means is using this interface, you can build standard components for these connections. Now, we can connect not only things to loggers and to the API for testing, we can also connect coverage subsystem in exactly the same way. And we've done that here where we have, we've got a source so people can have access to it, Verilog to coverage. So it goes from this tracer, when it's informed into different events going on, it basically can sample those, and it samples those into an instance class, a coverage class. So here, it's basically is passed in this case very simply the decode, which it then scanfs into and just gets in this very simple one there. It's just getting the mnemonic out. A more sophisticated one will allow you to separate them up for all the different instructions and different things, and then you can set your cover points in your SystemVerilog. So you can connect there through that. And the use of a standard interface for the DUT tracer means you can reuse standard components, and that's very important because that's a much more efficient way to do it. And a key component you could have is a SystemVerilog functional coverage system. And because RISC-V is a standard, they can be provided and made available. It's not proprietary to your specific core. And of course, if it's provided as source, which is what we're doing in Imperas, is providing that as source, then you can extend it for your DV specifics, for your specific microarchitecture to do with some pipeline issues or hazards or things that you're trying, real DV things. And we have an example of one that's available now, and we're going to shortly release others. So contact us if you want more information. And of course, once you've got SystemVerilog coverage, you can then, in the SystemVerilog simulators, they provide coverage reports so you can see exactly what's been going on in your design. And technologies like metrics allow you to basically measure that and see the status over time as things are evolving. So you can actually see how the quality is improving, getting up to the goals that you have in your verification plan. We're now going to move to the last section, the last component, and talk about instruction set simulators. There are five that I'm going to talk about, 5 subjects here. I'm going to talk about RISC-V OVP Sim on the GitHub, RISC-V OVP Sim Plus from OVP World. Then I'm going to talk about commercial technologies from Imperas and show 2 videos of that and then wrap up.
Okay, so now I'm going to show you the RISC-V OVP simulator. Now, what I've done is I've gone to the GitHub here, so you can see where it is, and we can see that we've come to the page here on here. And what this does is it includes the simulator itself, RISC-V OVP Sim, and also some tests and things in there. So RISC-V OVP Sim takes an application compiled as an ELF, it can do file I/O using semi-hosted file I/O. You configure and set up the model you want to run, and you get an output file. And when you're running compliance, you get a signature file for it in there. And inside the directory with RISC-V OVPSIM in the repository, you actually get the source of the model that comes with it, so you can have a look inside it and see how the instructions are created and implemented here. This is an example of a crypto instruction. And it comes with a full user guide, so you can see what's in there. And what you can see is the different versions of the specifications that are implemented in the model. So, for example, we have the basic sort of user and privilege modes, but also you can see here, the vector. We've had original 0.71 all the way through to the current one, which is pretty close to up to date on a weekly basis. The same with the bit manipulation, also the crypto, and we have all the standard stuff. And this version of the simulator actually doesn't have the hypervisor or the debug involved in it. So that's RISC-V OVPSIM. The other simulator, RISC-V OVPSIM Plus, is available from the OVP World webpage under the technology page, and that explains about RISC-V OVPSIM and RISC-V OVPSIM Plus. And when you go there, you can actually go to the OVP World page and download it, which is actually what I've done here. And so what I've got here is an example I'm going to show you. So I've downloaded it and gone into it. So first thing we can do is just have a look and see what sort of files and things are there. So this is the RISC-V OVPSIM Plus itself that you get there, and we can just run it up. And I've got a crib sheet on the left here so I can see, and we can get a help out of it. I've run the help command here out of it, and we can see the commands we've got for sort of controlling it when it finishes. We've got the coverage ones, debug ones for running GDB and things like that, all the way through down to the trace command, so that we can see how it runs. And we can see what's inside the simulator, which models are available sort of off the shelf. So these are all the sort of pre-configured variants that we've currently got in this example, this RISC-V OVPSIM. So we can go to the examples directory and see what's there. We've got a variety of examples that come with it. If we go into the Fibonacci one and have a look at that, we can see that. And if we can cat the file just to have a look at it, and you can see here that what we have is very simple, and it's sort of, you have a main in it, a program, and it will run. And then when we actually compile it up and run it, it actually simulates as you'd expect, and it runs through. It ran, that was 4.4 billion instructions there. So that's a simple example. If we go to the dry stones and have a look at that there in the example there, and we can just run it through, and it's going to run some 5 million loops through there. So it ran about 7 billion instructions there. So it's quite fast, this. And so just a few other features in there. We can run tracing, put that on it, so we can actually see the trace, and trace the OVPSIM traces are very sort of configurable in that you can see here. We're seeing which mode we're in, the disassembly, what the instruction count is, and things like that. We also have the ability to run up a GDB with it just by putting a GDB on the end of the command here, and then we can we've got access to a GDB to run the simulation, to control it and debug it and do what we like with that. You could use an Eclipse-based thing or anything. And it also, the simulator has a basic coverage analysis in it, which it can simulate. Here we just ran I think 10,000 instructions. We get basic coverage, and we can actually have a look at the coverage file and see which instructions and which operands and everything we used for that. So those are the basic free RISC-V OVPSIM and RISC-V OVPSIM Plus simulators. And now we're going to have a look at some of the Imperas commercial technologies, the simulators, and then the virtual platforms which simulate the whole virtual platform, the emulation, the system emulation. So I'd like to just show you some of the Imperas technologies. So I can go to the Imperas website here, imperas.com, and look at the products. So in here, so I can come and I can look in here. The first thing I want to do is to look at the simulation that we've got here. So let's have a look at the simulation that we've got here. So there's several pages. I'm not going to demonstrate too much of this, but we've got the simulator, explains how it's done, explains how it's built, and it also talks a little bit about the performance and debugging. And we can see it's a very fast simulator, and you can look at this. We support a whole lot of different processors out there. These are the main ones. Obviously RISC-V, 32, 64-bit, very, very fast there. And what we've also got in here is a variety of different tools. So the first thing to look at is we have a debugger, which can come with it, which works in sort of three ways, in that it can look across the design, across the platform components. It can look across time, so it can trace things over time and have set assertions based on time, but also it can look at an abstraction. So it's a pretty sophisticated debug tool. And the way the system works is you run the simulator with the simulation models there, and then you have a variety of different tools that can work it. And one of the areas that we've got tools is in verification, analysis, and profiling. And if we look just up here to that, we see here that we've got in our verification, analysis, profiling tools, we've got tools to trace sort of function calls, profiling, where all the different time is spent in the execution of the programs, through to instruction profiling and code coverage and things like that. Now I'm just going to give a little demonstration here of some of the things that we've got. So the first thing I've got is a very simple example. So if I'm just going to go to our Imperas installation, and we have a demo directory which here has processors on it. I'm just going to go, in this example, I'm just going to go into a Sci5 one. We've got a variety of different families there, and if we look at the U7 lot, we'll see that we've got a U74 in there. So let's have a go in there and have a look at that. We'll see again we've got a lot of examples to provide there in there, and what we can do is run different things. So this is a simple processor running, a simple example running a processor and executing that. So I'm just going to run that on an example to show performance. So this is an integer register operation program. So running 28 billion instructions there, ran over 9 billion instructions a second on my regular desktop. So it's extremely fast. So that's running a single processor on a single machine. What I can also do is run my different cores in a simulation actually on the different cores of the host machine. So if I go into another directory here, we'll see we've got several examples. And here, instead of just running one processor in a simulation, we can say actually run 4 processors. So it sort of duplicates that up. So if I run that, so I'm running 4 processors in one simulation running dry stones, and we'll see that we still get very fast simulations. This is running 4 million loops for each one. So again, we've got 4 different processors running in the simulation. Each ran 5 billion odd instructions. So overall, we saw 20 billion instructions go through. So that's pretty good. So now what I can do is I can actually run it in our the quantum leap, our parallel mode. So we're running each processor actually in the simulation on a different host core on my machine. Again, same amount of events, same simulation, this time extremely fast. So that's a much faster way to do it. So the Imperas tools give you fast simulation, very sophisticated debug, a lot of verification and analysis. We have several examples that we can show where a model can be run in a platform with an operating system running. First one we're going to show is an Andes model running. So it's an Andes N25 going to run with some memory, timer and some UARTs, and that's going to run the free RTOS in there. So obviously up and then there it's running, and it's actually just writing to the console here, to the UART. There wasn't any input I could do, and we ran some almost 9 billion instructions. So it's very fast, running at about effectively a gigahertz, which is pretty good for an embedded system in there. So let's have a look at a different example here. This time, this one's a Sci5. This is a multi-core one. So this is where we have an FE540 type of board here with a virtual platform with 30U54. So it's a multi-core processor running. So we run that. You can see there it's booting Linux in this console. Once it's booted Linux, I need to get in there and type that. I've got the password in there. So what is it? Cat dash. You can see there's 5 cores in there. We can run it. We can see it's an operating system running. It's very fast and efficient. And it was running on multiple cores there. We didn't run too long, but it's very quick and efficient. And just to wrap up, so that's a multi-core platform. Actually, you can run a heterogeneous system as well with our simulation environment. For example, this is an example of an AI machine learning processor that one of our customers is working on, which has multiple RISC-V cores, 64-bit GCs. There's actually 17 or 18 of them there, and it also runs with an ARM controller in one simulation. And we can run that up here. And while that's running, I mean, we can see, the type of thing we're going to run is actually a neural network going through it in here. And so it's running, and there's actually a console which is doing convolution and doing the different things for you there, which I can, if I kill that here, we can see that there's 17 hearts and 17 processors, not to that, running with an ARM. So we can do heterogeneous simulations as well. So in terms of an ISS, a simulator summary, so we've only mentioned really the Imperas simulators here because we use those on a daily basis. Our customers rely on them. We really understand their quality. But of course, there are others out there. Pretty much any grad student can build an open source simulator. Just go search GitHub if you want them. I mean, RISC-V has a formal model under development written in the SAIL language out of Cambridge University. There's also Spike from Berkeley, which is an architectural exploration simulator. And there are a full system software emulators like Imperas. QEMU is an example of one of them. And what we showed you here is really a couple of the free simulators from the GitHub, RISC-V OVP sim, which is really useful for sort of compliance level work. And then the RISC-V OVP sim plus, which is really for the more detailed simulations because you can get full trace and debug out of it. And that can be used in the Google RISC-V DV instruction stream generator flow as a post-simulation trace compare reference in there. And then we just showed you a couple of things around the Imperas tools where we have a full range of ISSs, virtual platforms, full system emulation, extendable platforms where we have hundreds of models, components and peripherals, and can simulate an awful lot of operating systems running on top of them. And now I'd like to summarize this tutorial. So congratulations on getting to the end of this tutorial. And if you got this far and still have some energy, send us an email to that address and with the subject as listed there, and we'll send the first 50 one of our Imperas DV drinking mugs as a thank you for persevering and going through this, and we're sorry not to be there in person. So what we covered in this tutorial was a brief introduction to RISC-V. If we'd have had longer, I could have explained more, a little bit about the DV approaches people are using for CPU, and then some of the components that you'll find in those environments. In terms of the hardware DV approaches, we actually looked through Hello World, which obviously isn't a DV environment, through to self-checking, post-simulation, trace log compare, several synchronous and asynchronous approaches in there, the use of standards and the evolution of this RVVI, RISC-V verification interface, and then we walked through a 35-minute walkthrough on a simulation and verification technology we've been building in Imperas DV that our customers are using to help with the verification of RISC-V. We then went through the different components, through the compliance tests and test suites, through the instruction stream generators, a little bit about functional coverage, and then through some of the Imperas instruction set simulators and tools. What we did not talk about is the use of our technology within sort of SystemVerilog general simulators, which can be used with RTL emulators, including hybrid. And yes, we do that. We have customers doing that. We didn't talk about formal tools, key part of verification, which we don't do those. So in summary, RISC-V, being an open standard, offers many design freedoms. And what this means is there's huge amounts of verification going to be needed. And the key thing is to find discrepancies and debug those efficiently. And the RVVI interface offers a framework for that. And the Imperas tools out of the box means that you can get started with your verification. Thank you.
Hello there. Thanks very much for watching that. I'm going to just sort of wrap things up here a little bit. Hopefully you can hear me all right there. We've been answering questions as we've been going on the chat. And actually, some of them have come to us individually rather than to the main ones. We couldn't work out how to get them into the main ones. But the last one here that's on there is from Nitin. So it actually has 3 questions in it. So that's probably a good one to use here. So is the synchronous, let me just bring it so I can see it here. So is the synchronous DV approach free open source to use outside of the open hardware group? And how good is it for RISC-V vector processors? Okay, so that's 2 questions in that one. So the synchronous DV approach. So what we've covered here in this presentation is the different approaches people have taken. And yeah, so a synchronous approach is where basically on instruction retires, you compare what's coming out of the RTL or DUT with a reference model. Yes, you can, anybody can do that. The approach taken in open hardware actually uses an Imperas reference model in there. So everything but the Imperas reference simulator is actually open source in there, but the Imperas reference simulator is not open source from Imperas. You have to come to Imperas for that. And in terms of vector processors, so vector processors, I guess, is a relatively new thing that people have been verifying. I alluded when talking about the tests earlier on that actually a couple, 3 years ago, we were engaged by a company doing a very large vector process to help them write tests and do verification. And you know, so we've created a lot of tests and there's quite a lot of experience in using those tests. When it comes to the verification of vector processes in RISC-V, there are several options that are configurable in the specification. For example, what happens with interrupts and exceptions and things. So it can get very complex. So you really can't put testing a vector processor in the synchronous approach. Some people are trying to just run the vector engine as an application on the back and just comparing and testing that. That's okay for the basic instructions, but a real vector engine has asynchronous behavior, or could have, and that would be a lot more complex. So that answers the first question. Second question would be, which would be better for a basic vector process setup, sync, lock, and compare, or async? So I would say that synchronous would not be good enough for a vector processor unless the vector processor cannot have any asynchronous behaviors in there, which I'm sure they do. Okay, and the RVVI used in the open hardware project can't look. Yes, it's not in the IBEX core. Yes, if you look at, I will post on the chat if I can find it quickly here. The basic place you want to go to is the open hardware's Core 5 verif in the, so there, and the processors CV32E, 40, X, and S both use the RVVI interface in there, so you will be able to find that. They basically layer from an RVFI, because those guys are using a bit of the formal stuff, and they layer up into that. So I think those, I'm sorry, I've sent that to the wrong place. That's the link. And those are the 2 cores that use the RVVI. So I think with that, with no further questions, I'd like to say thank you very much for attending. Obviously, it's been a marathon session, 2 hours. But this is a very complex set of issues, testing a processor. And I think a lot of people are making a lot of good progress in evolving the methodologies. And so thanks for your attention. If you've got want more information, send us info@imperas.com and we'll answer your further questions. So with that, I'll say thank you very much and sign out. Thank you.